So lesson 6.5 is going to focus on geometric sequences. But before we talk about geometric sequences, I just want to lay a little bit of groundwork to make sure we're all on the same page as to what do we mean when we talk about sequences. So just, remember, if I write it down, you write it down. That way this is in your notes. But a sequence is officially just an ordered list of numbers. So let's write that down. So it's an ordered list of numbers. And they could have all kinds of patterns. So this is an ordered list of numbers, and by ordered we mean there's some sort of rule or pattern establishing what each number is going to be, in the list. And so there's an infinite, possibilities as far as what kind of sequences you could make. You could be as simple as 1, 2, 3, 4, 5, just a list of whole numbers. That can be a sequence. There's some more complex ones. Possibly one that you've heard of that's kind of famous is the Fibonacci sequence, if you've ever heard of that guy right there. So Fibonacci is pretty exciting and famous. And a big part of that is the way that it tends to come up in nature naturally. But the Fibonacci sequence looks something like this. Just to give you an example, it starts with 0, 1, 1, 2, 3, 5, 8, 13, 21, and so on and so on and so on. And if you don't know what that pattern is already, kind of look at it and see if you can kind of figure out how is a Fibonacci sequence developed and what might be the next value. But that's a famous example, but one of, like I said, so many that I could come up with here of a sequence. It's simply just an ordered list of numbers. You could make a sequence of even numbers, 2, 4, 6, 8, 10, 12, and so forth, right? So I just want to make sure you understand what a sequence is. And to go a little bit more into detail, each number in the sequence is usually called a term. Okay, and we talk about a lot like what the position is, right? So this is the first term in the sequence. This would be the second term in the sequence, the third, all the way down, and sometimes we just leave a variable all the way to the nth term, especially when we're writing equations like we will later. That n will represent the nth term in the sequence, right? So we call these terms. So just a little bit of background there. A list of ordered numbers, and then each number in the sequence is considered a term. We really focus on just what the position is of that term. N is here is going to represent the nth term. Okay, all right. So now that we have talked about that, today we'll focus primarily on geometric sequences, although I am going to bring up just a little bit about arithmetics so that we can do some of these problems. But in a geometric sequence, the ones that we're going to focus on today, the ratio between each pair of consecutive terms is always the same. Now remember, ratio, that means a comparison by division. So essentially that means that if we were to take the ratio of each consecutive value here, 5 over 1 is 5. 25 over 5 is 5. 125 over 25 or divided by 25 is still 5, right? And so in a geometric sequence, that is the defining characteristic, that type of pattern, okay, where the ratio between the pair of consecutive terms is the same. This ratio is called a common ratio, okay, and then each term is found by multiplying the previous one by whatever that common ratio is. So if I see a sequence and I test this out, and I say, okay, let's see if this is geometric. I do 5 divided by 1 is 5, 25 divided by 5 is 5, 125 divided by 25 is 5, and I can establish that my common ratio is 5 at that point, then I could use that to extend the pattern and keep this list going. Once I've realized, oh, they're multiplying by 5 every time, if I wanted to know what would come after 125, I just have to multiply by 5 again and get that result. Okay, and you could just continue doing that. That would define what the rest of the values would be in that sequence. Okay, if that looks familiar, that's not a coincidence, right? So we're actually following this right after exponential functions. because geometric sequences are very closely related to the exponential stuff that we've been talking about, because they have that multiplicative pattern, okay? They're multiplying repetitively. All right, so one thing is to find out that common ratio and then be able to use it to extend. And that's wonderful. It's important to know what the common ratio is. It's helpful to extend it if you need a few more terms. But the reality is that maybe I don't want the, this is the first, let's see, this is the first, the second, the third, the fourth. Maybe I don't want just the fifth or sixth term. What if I wanted, I don't know, the 719th term? All the way down, right? Nobody wants to have to extend and just keep going on a pattern all the way to 700, whatever I said, 719 values. Nobody wants to do that. And that's where this guy comes in, right? This equation right here for geometric sequence, important, right? Lets you find the nth term of any geometric sequence as long as you know what the first term was and what that common ratio is. So as long as you have those two ingredients, what number did I start at and what am I repetitively multiplying by, then this equation right here lets you find any term, even if it's way down the line. I don't have to sit there and just keep extending the pattern all the way down. I could find the 37th term in a snap, or the 14th term, or the 53rd term, right? With a function, with an equation like this, if what we have is a geometric sequence, okay? And again, I'm gonna mention it one more time. If this looks familiar, if this feels a little bit like deja vu from when we did y equals a times b to the x, you're not wrong. Okay, it is a similar setup, except we're looking at it through the lens of sequences. But we have a first term or a starting value, and then after that, we are repetitively multiplying by that common ratio a certain number of times, right? The big thing I want you to notice is that our exponent is not going to be just n, it's going to be n minus 1. So if I wanted the 53rd term, I would do 53 minus 1 here. My power would actually end up being 52. Okay, so we'll practice that in just a little bit, but keep this guy in mind, because this is your friend. Anytime you're not just extending one or two, but you want to jump ahead, this is what you're going to want to work with when you have a geometric sequence. Okay, but before we get to that, let's talk about just being able to identify. We're going to start off easy and slow. Okay, and so it says in exercise 1 through 6, we're going to determine whether the sequence is arithmetic, geometric, or neither one, and explain why, or just give some sort of evidence. So you might be like, wait a minute, what is that over there? Well, you haven't talked about that, Ms. Shireda. And you're right, I have not. And we're going to actually spend a whole day and a half on this, within the next 24 or 48 hours. But right now, this is what I'm going to say to you. So arithmetic is a different type of sequence pattern, that instead of it having a multiplicative pattern or a common ratio, it has an addition or subtraction pattern. So let's kind of make a note on that. So arithmetic means essentially that there is a common difference, or just a common difference between the pairs. So it means an addition or subtraction pattern. And we're going to spend more time kind of diving into that. But just like this might really make you feel like, oh, that looks a lot like the exponential stuff we were doing. When we do end up talking about arithmetics, you're going to think like a linear pattern, because that's what happens in linear equations, is we're repetitively adding or subtracting, right? So this is going to have a kind of a linear equation feel to it, where this has an exponential equation feel to it. And so they have some similar characteristics to those functions that we've studied. We're just looking at it from the sequence point of view. Okay, so when we're looking for patterns here, if we notice that they're adding or subtracting, then we're going to call it arithmetic. Okay, otherwise, if it's multiplication or has a common ratio, like we talked about up here, we're going to call it geometric. And perhaps, maybe it's a Fibonacci sequence or something else. It's neither geometric nor arithmetic, and then we'll just say it's neither one. Okay, so let's try a few of these. if you check on number 1, the first thing I'm going to try for is geometrics, because that's what I'm most interested in. So I can take this information right here and see if I have a common ratio. So to do that, I'm going to take these 2 consecutive terms and put the new over the original. And I know that gives me -4. And then test to see if I get the same thing here. And if I do, then I know that I'm on the right track. So 16 here divided by the -4, and that's a -4 again. Okay, so let's see if we have a common ratio here. I've got a -64 over 16. Hey, that's -64 as well. So I do have a common ratio. Every time I compared consecutive terms by division, I got the same number every time. And what that tells me is that this is geometric, and that common ratio is -4. Okay, just like up here, it was at 5. If I wanted to extend this pattern, I could do that now, because now I know that they are repetitively multiplying by -4, so I could do times -4 and get the next number, times -4 again, get the next one, and so forth. Okay, all right, so let's try number 2. If I try the same thing with number 2, if I run the same test, I can do 7 over 3. Well, that doesn't simplify, it's just 7 over 3. And then I could try this ratio right here, would be 11 over 7. Well, I know enough to know that those are not the same ratio. This does not simplify to that. They're not equivalent. If you're not 100% sure, you'll feel free to grab a calculator and actually perform this division. And you're going to notice it gives you different decimals. So this is not geometric. So we can look to see if perhaps it has a different pattern. So let's try for an arithmetic pattern, which would be a common difference instead. So this is a no-go. So and then let's try a difference. If I do 7 minus 3, I get 4. And then if I do the 11 with a 7, and if I do 11 minus 7, I also get 4. And then if I do 15 minus 11, I also get 4. So you might have already seen that. I'm just being super formal about it, but you might have already seen, oh look, they're not multiplying by anything. They're adding 4 every time. Okay, so because this is an addition pattern where the sequence is being generated by adding the same number every time, plus 3 plus 4 is 7, 7 plus 4 is 11, 11 plus 4 is 15, then this is arithmetic. Because that's arithmetic sequences are the ones that have an addition or subtraction pattern. This is arithmetic, and that common difference would be the 4. And in fact, I could use that 4 and extend this and realize, oh, the next number is going to be 19, and the next one would be 23, and so on if I wanted to extend it a little bit further. Okay. All right, let's try this next one. On this one, let's try the common ratio again. If I do 4 over 2, I get 2. If I try 8 over 4, I get 2. Okay, that's good. If I get 32 over 8, I get 4. So I don't get a common ratio here. I'm glad I tested all the way through. So that is not geometric. Okay, so that doesn't work. Then let's try arithmetic. Are they adding the same number every time? Is 4 minus the same thing as 8 minus 4? Nope, it's not. And definitely not the same thing as 32 minus 8. That's not going to work either. That's 24. So it's not arithmetic either. Okay, so doesn't have a common ratio. That means it's not geometric. It does not have a common difference. So it's not arithmetic. We're just going to say this one is neither. Okay, it's neither one. It's some other pattern. Obviously, it's still a sequence, and there's some sort of order or pattern generating it. It's just not one of these two cases that we've been playing around with. Go ahead and pause the video here and try 4, 5, and 6, and then you can press play and see how you did on those. All right, and hopefully that gave you enough time. Number 4 is neither. So it looks like here the ratios are not the same, and it looks like it decreases by 3, and then by 2, and then by 2. So it's not a common difference or a common ratio. I got neither for that one. Number 5 did have a common ratio. 18 over 6 is 3. 54 over 18 is 3. 164 over 54 is 3. So that's geometric with a common ratio of 3. That's what they're multiplying by every time. And on number 6, you're looking at arithmetic one. I looked at the common ratio. It did not work. But when I did 19 minus 11, I get 8. 27 minus 19, I get 8. 35 minus 27, I get 8. And so it's the arithmetic style sequence with a common difference of 8. They're increasing by 8 every time. So tomorrow, we'll really spend more time going deep into the arithmetics. Here, I just wanted you to be able to differentiate what makes something geometric versus either arithmetic or other patterns, okay? So, and we're focusing on geometrics. Well, that's our lesson, obviously, but just because it ties nicely into those exponential types of relationships that we've been doing, okay? All right, so let's take a look at this next page on the back, okay? Here, we're just going to practice extending patterns in a geometric sequence. So I want you to notice, first of all, that they already called this geometric, which is good news for us because it means we don't have to prove it, decide if it is, we don't have to test it. It's a geometric sequence. It has a multiplicative pattern, and that's already been established. So if I can just find that common ratio, then I can use that to extend my pattern as necessary. And I can find the common pattern by just taking any of these and doing that division of the new term minus the previous term. So if I keep it simple, perhaps I grab these two consecutive ones, the first two here, 21, 7, I know is 3. So that tells me my common ratio must be 3. That means they're multiplying repetitively by 3 every time. And in order to get the next 3 terms after 189, all I have to do is continue to repeat that pattern of multiplying by 3. So let's say that we start with that 189, and I take that times 3. The next term in my sequence would be 567. And then if I want to continue to the next one, I just repeat the same pattern again. Just multiply that by 3. And the next value is 1,701. And it asks us for 3 of the next term, so we'll do that one more time. And our next value is 5,103. Okay, so those would be the next 3 terms in the sequence for number 7. Okay, let's try number 8. On number 8, to find R, which is the most important thing that I need here, I'm going to do the ratio of consecutive values. So I'm going to do 288 over the 576. And when I do that, so when I do 288 over 576, let's see what we get. 76 there. And so when we divide that, we get 1/2. So that's our R value. They're multiplying by 1/2 every time. That means we're just taking half of each number. So if we're at 72, if I extend this pattern for the next 3, half of 72 I know is 36. Half of 36 will be 18. Half of 18 will be 9. So those would be the next 3 terms in that sequence. And then let's take a look at number 9. I think this one's interesting and important to do because when you look at what R is here, or just what's even happening in this particular sequence, hopefully it jumps out at you that the signs are alternating here. You got a positive 5, a negative 10, a positive 20, and a negative 40. And the reason for that is when you find R, you find out it's negative 10 over 5, which is a negative 2. Okay, that means that your R is negative. When you see a flip-flopping sign like this, that is a dead giveaway that you have a geometric sequence with a negative ratio. Okay, if you check it, you'll see that works. It's 5 times a negative 2 is negative 10. But then negative 10 times a negative 2 goes back to a positive 20. And then a positive 20 times a negative 2 goes back to a negative 40. And it just keeps kind of flip-flopping the sign all the way through. Okay, so our R value here is negative 2. That lets us continue the pattern. So negative 4 times a negative 2, the next one will be 80. And then 80 times negative 2 will be a negative 160. And then negative 160 and times negative 2 will be a positive 320. So you see that pattern of flip-flopping signs continue. That was kind of a deal breaker if you remember when we were doing functions, when we were looking at this from like the functions and equations and graphs, you weren't allowed to have a negative b value, the multiplier, right? But in sequences, that's totally fine. It's just an ordered list of numbers. There's a lot less rules here. And you're welcome to have a common ratio that's a negative number. That was kind of a deal breaker for exponential functions, and it still is. But you can do that in a geometric sequence. So not everything is the same, is kind of what I'm getting at, okay? All right, so if we feel good about just extending, using that ratio to just extend patterns out, then let's do a couple of graphs and finish out with finding nth term with the equation like I had promised, okay? So if you were to write the next three terms and then graph it, let me explain to you what I would mean by. So the first thing that might jump out at you is, well, how do you graph if it's just one list of numbers? Okay, well, that's a very valid question. The way that we do that, since we need, two numbers in an ordered pair, is that we are going to graph our sequence based on the position of each term. So when you're looking at a sequence here, especially if you're going to graph it, I want you to think of it more as like a table. Again, if I write it down, you write it down. Where n, or you could even call it x if you like, but a lot of times we use n in sequences, where n is the position of the actual term. So in first position, we've got the number 12. In the second position, we have 6. In the third position, we have 3. In the fourth position, we have 3 halves, right? And they want us to extend, so we may as well just write it out. We'll want the 5th, 6th, and 7th terms, okay? And so where we call this n, the term in the sequence, this is a sub n. You already saw the a on the other side of the page here, and that's the actual value in that spot. So when we graph these, we're really graphing them based on where their position is. Like if my first term is 12, then on my x-axis, I would go to 1 because that represents the first term. So this axis represents what term in the sequence it is. Okay, so this is the n, or the term in the sequence. Term in the sequence, right? And then this is actually the value or the number. So sequence value or sequence number. Okay, and so first of all, let's extend it. Pretty quickly, you can probably tell here that our common ratio is 1/2. 6 divided by 12 is 1/2. 3 divided by 6 is 1/2, and so forth. So we're going to continue taking halves here, or multiplying by a half every time. So let's extend here. If I do 3 over 2, and I multiply that by a half, I get 3 over 4. And if I do 3 over 4 times a half, I'll get 3 over 8. And then if I do 3 over 8 times a half, I'll get 3 over 16. And this is why fractions are better. Just saying. Okay, that was a 2. All right, and so now that I have my sequence, let's go ahead and graph it. I think I'm I only have to go up to 12, so I think we're gonna be okay. This is gonna be the first term, second, third, fourth, fifth, sixth, and seventh terms in the sequence. I'll label the rest, but that's as far as we're going to go. And then, you know what? I wonder if going by 2s would be better on this one. That's what I'm going to do. I'm going to go by 2s. No, I think this is fine. I don't think it'll fit otherwise. Or will it? 10, 11, 12. Yes, it will. Make these decisions here on the fly. Let's do it. Well, if I could erase this. This is why pencil's better, y'all. Oh, I'm out. That would be why. All right, let's try this again. So I'm going to go by 2. So 1, so first term, second term, third, fourth. Let's see if I don't mess this up. This is the 5th term, the 6th, and the 7th. Ah, perfect. Okay, and then we want to go up to 12. So these are definitely go by 1. So I'm going to count by 2s, but I'm going to go up by 1s. That's 10. Okay, so the first term in my sequence is 12. The second term in my sequence was 6. The third term in my sequence is 3. The fourth term in the sequence is 3 halves, or 1 1/2. And then the fifth term in the sequence is 3/4, or 0.75. starting to estimate here. The sixth term is 3/8, or 3 over shy of a half. And then 3/16 is about a fourth, but it's going to be down here. And you can just see the pattern there. And again, I'm going to say it one more time. If that looks familiar, it should. It very much is similar a lot of times to an exponential curve. Not always, though. This one wouldn't be, right, if I graph that. But the ones that are the same sign usually look like an exponential like that, okay? All right, so I'll let you guys, we might try another one of these. Probably I'm going to circle number 12. If y'all try it, we'll talk about that one in class. I want to get to the crux of this, which is this lovely equation that we had on this page right here. Oh, I flipped it. This guy right here that lets us jump over, because that's more realistic, right, than just extending a couple of values. It's really being able to jump down the line, okay? So in this set of exercises, and we'll do a couple of these and we'll finish the rest in class. We have a sequence. We were told that it's geometric, and we want to write an equation for what the nth term would be, then use the equation to find the sixth term in the sequence. So that's what that means right there. It says then find a of 6. That means the term that is in the sixth position. That's what that means, okay? But first, let's write our equation. So just a reminder of what that equation is. It's right here on the front, but I'm going to write it here next to us. So you can find any term as long as you have the first term times that common ratio to the n minus 1. So that's what we're going to use as our template. For the first part of this, I want to write an equation for the nth term. So I'm going to leave the n's ends. That's important. So in part A of this, if you will, I'm going to just say, okay, so the nth term in this sequence would be, or the equation for that would be a sub 1, which is this first term. So this is the first term in my sequence right here, second, third, fourth. So it would start off at 6,561, and then times the common ratio. So that we have to figure out. So if we grab a calculator and we divide and do that ratio all the way across, 2,187 divided by this, 729 divided by that, or that divided by that, we're going to realize it's always 1/3, 1 over 3. So that's our R value. And then our exponent would be n minus 1. And that is all you would want to do, and I would want to see that as kind of the first part of your answer, is just the generic equation to find any nth term. So that would be our equation there. Once we have that, then kind of for part B here is actual solving this for the sixth term. And I know that 6 isn't too far off, and you're like, well, maybe I could just cheat. Don't cheat. I want you to know how to use the equation for it and get used to that. So if I want the sixth term in the sequence, now n becomes 6. The first term is still the first term. That doesn't change. My common ratio is still the common ratio. That doesn't change. But I'm going to raise this now to the power, which is 6 minus 1. In this case, that's a power of 5. And then I can reach for my calculator and see what that actually gives us. So let's give that a try. So once I have that information in, I can say, okay, starting value, 6,561. My common ratio is 1/3, and I'm going to raise that to the fifth power, or you could even like write this in like that, and that's usually okay. It turns out that the sixth term in this sequence would be 27. Okay, so our answer here for the sixth term would be 27. Okay, let's try one more. Perhaps we try it from a table this time. So let's try number 17. Let's jump down to that one. And I think we're going to finish off with that. So on number 17, you have, let's first write the equation. So for part A here, we're going to write the nth term equation. So for that, all I need is to know, what did I start at? What's the first term in the sequence? 11. And what is the multiplier, right? The common ratio. So you could take any of these numbers, like 7 divided by 176, and I would realize, oh, the common ratio is 4. And 11 times 4 is 44. That times 4 is that. That times 4. So I'm repetitively multiplying by 4. That's that common ratio. And then this stays n minus 1. And that's my answer for part 1. That is the geometric sequence equation for the nth term in that sequence. Then for part B, I would want to evaluate this for the sixth term. And so I would take my equation, plug in a 6 for my n's here to know what term I'm looking for, here to actually solve it. And let's find out what that is. So we're 11, 4 is our base. We're going to raise this to the 6 minus 1, or just a fifth power, however you want to write that up there. And that would be our sixth term in the sequence. Things grow fast, right? So it would be 11,264. So 1,264 would be the sixth term. And you can do that from a sequence. If the sequence is written as a table, you could still do it. If the sequence is given to you as a graph, you can still do it. Any one of those will work. Let's finish out with number 20, since we haven't seen one like that. This one definitely doesn't have that curved shape. And right away we can see why. It's because the first term in the sequence is 8, the second one is -4. Then the third one is 2, the fourth one is -1. The fifth one is 0.5, so you see that flip-flopping sign, that zigzagging across, and that's why it doesn't have that curve shape. That's still a geometric sequence though. They just graphed it, and we can still pluck out the information we need to write our equations. So to find the nth term of any value here in this sequence, all I need to know is what was the first term in the sequence? Well, the first term in the sequence is 8. What is the common ratio? So what I'll do is I'll take two consecutive values and divide them. So if I do -4 divided by 8, I realize it's -1/2, right? And I could do that for any of those, but it's a -1/2 common ratio here. And you could do a decimal too if you really want to, no big deal. Okay, and then last but not least, there's our equation. Let's solve it in the second part for the sixth term. So first, started at 8, still have a common ratio of 1/2, but I would be doing to the 6 minus 1 power, which is a power of 5. Let's see what that would give us. Oh, no, not divided by, raised to the 5th power. Looks like it would be -0.25 would be the sixth term in this sequence. So -0.25 or 1/4. Well, but they did decimal, so let's do that. 0.25. That would be the sixth term in that sequence right there. I'm going to rewrite that. -0.25. All right, and that is geometric sequences. They are an ordered list of numbers that have a common ratio or a multiplicative pattern generating each of the additional values.